All right. Yes, we are live. Change the title. We changed the title for bring this. Right. Yeah. I guess probably I will need to. Okay. My colleagues that are online, can you give me a thumbs up if you can hear things well? Thanks, Marielle. All right. Are you guys ready to rock and roll? Okay. Lucia, can you close that back door for me, please? So we will see well. Okay. Good morning, and thank you, those of you that are both in the room and online, for joining us today. It is my absolute pleasure to introduce you to this year's cohort, I guess is the right word, of teacher candidates taking the ECUR from Curriculum Studies 411, which is an inquiry-based teaching level class. They have been working really hard in the fall term, and they have some really interesting things to share with you. And it will give it impact. Who go first? I need to share from that computer. I need to make that computer okay so that you can share, I think. Try and share. Are you sure the presentation? Yeah. Right.
So, hi everyone, welcome to our ECUR 411 presentation. We've titled it "The Real Jewels Are the Friends We Made Along the Way," which you will understand when the presentation is over. Before we start, we'd like to acknowledge that we're gathering on Treaty 6 territory and affirm our relationships with the land and with one another. We recognize the affordances of the lands on which generations of our families have sustained themselves, and we bring our knowledge of teaching and learning and recognize the ways in which land has allowed for these practices to occur.
So all kinds of technical issues today. We're good.
Introductions. We'll go over the context and the background for our presentation. We'll talk about evidence and results, and then we'll go through some future considerations. So to start, my name is Oliver. I am in my 4th year of education. My teaching areas are math and physics, and I have a bit of a background in science before coming into this class.
My name is Ethan. I'm also a 4th year education student with teaching areas in math and drama. And I took this course because I was really interested in synchrotron science and kind of what that looks like. So I was really excited to be able to do a project in this space.
Good morning, my name is Janelle. I'm also a 4th year education student with a focus on secondary education with a major in biology and a minor in French. And I'm also really grateful to be here. I've been a student on the Beamline project in grade 12, so it's been a really full circle experience.
And I'm Mike. I'm also in my 4th year. I'm in my 4th year and a little nervous. There's so many people in here. My teaching areas are math and biology. I have had some experience back in high school doing this in the Beamline. Yeah, that's our group.
Okay, so a little bit more about what brought us all together. So ECUR 411 is a curriculum studies course for 4th year students that takes place after we have all completed our internship. So we spent the fall teaching in Saskatchewan schools, and this course gives us the opportunity to work both as educators and as learners. which is a very unique process and not like any other Bachelor of Education courses. We get to reflect and investigate new pedagogical approaches and reflect on our teaching experience. And then as students, we get to design our own project and work here at the CLS. A bit more on the terminology. So pedagogy refers to the arts and science of teaching. It focuses on the how and the why, and it discusses or involves things such as assessment and instruction of students. And a specific pedagogical approach is inquiry-based learning that we experienced in this course. It is a very active and hands-on learning experience that places the student at the center of the learning. And it challenges students to pose questions, make observations, collect data, and pull conclusions from what they've seen or found. And overall, it just places the curiosity and questions of students at the center of the learning.
So before we get into kind of the main details of our research, we wanted to kind of outline both the pedagogical importance of our project and also the scientific importance. So overall, participating in an inquiry-based project brings light to some practical applications, both for us as future educators and also how we can apply it into our future classrooms. So that's something we're getting into. And also we were able to, like Janelle said, gain knowledge through both the lens of an educator and a student. So throughout the term, Tracy would refer to it as kind of switching hats from, thinking as a teacher and then thinking as a student as well. So being able to kind of think in both of those domains helped us gain kind of a more fulsome understanding of both the research project, but also inquiry-based learning as a whole. And some scientific importance. So we were looking at jewelry, and we kind of wanted to see if there were any impacts on sweat when you are sweating and you're wearing jewelry, and are there any metals that kind of leach into your body from the sweat? So there is actually scientific evidence that metals do leach into human sweat and it can be harmful. So we wanted to look kind of at some different jewelry and artificial sweat solution and see if that was actually a thing that we could find. Another thing that we wanted to kind of outline for our importance of our research is through doing a little bit of research on metals and kind of the availability of metals, Indigenous communities in Canada are disproportionately exposed to environmental contaminants compared with the general population. So some metals might have contaminants in them that if it is present in jewelry, then could have some sort of negative effects. And 29% of contaminated sites in Canada are on reserved land. So we wanted to see if there was kind of a direct correlation between our topic and any negative effects, both in Canada, but also in Indigenous communities, since there are these stats that are quite staggering.
So for anyone who's not familiar with what the CLS is, it stands for the Canadian Light Source. It is a national research facility on the University of Saskatchewan campus, and it is Canada's only synchrotron. So it's really cool that we happen to be here and we get to use this really awesome thing to do this research. It's really unique, and it creates a different kind of light that you can use for a lot of reasons, including studying the structural and chemical properties of materials. So this is a little diagram of what the inside of the CLS looks like. So there's this big ring in the middle, which is just out there, and then all these smaller lines that come up here. And the idea is that they have electrons that go around this middle big ring right here, and as they're moving and turning, they emit photons, and then they direct those photons down the lines, which are called beamlines. And so the beamline that we used, probably hard to see, but it's right here. The beamline that we used is called IDEAS. So it stands for Industry Development, Education, Application, and Students, and it's dedicated to industry development and educational purposes. So the technique that we specifically used was called X-ray fluorescence. So it uses high energy X-rays to essentially probe the elements that might be present in a particular material. So the photons that are directed down the beamline, the IDEAS beamline, are X-rays. And then what we did is we put our necklace and then also a sweat solution that we made, and we put it in the beam of these photons. And the elements in the material would absorb the X-rays, and the X-rays or the elements would emit another X-ray that was characteristic of what type of element had absorbed and then emitted it. And then we were able to tell, based on measuring how many of these photons were emitted by the atoms, what atoms might have been there. So we were able to get, after doing all of this is just a sample graph, an XRF spectra is what it's called. So you'll see a lot of graphs that look like this. Don't worry about what these titles at the top are, but the idea is here's a count of all the photons that are emitted by the different elements, and then down here is their energy, and based on how many of what energy there are, we can say what kind of elements are present. So that's a bit of the science between or behind the techniques that we used to probe the metals that might have been present in this wet solution.
So guiding a bit more into what prompted us to do this research is we came across some regulations within the country regarding jewelry. So the Canada Consumer Product Safety Act regulates consumer products to prevent dangers to human health and safety. And within that, there is the industry guide to children's jewelry, which places specific limits on both lead and cadmium that can be found within children's jewelry. So that applies to any jewelry that is manufactured, sold, advertised, or imported within Canada. However, we saw that this only applies to jewelry intended for individuals that are under the age of 15. So adult jewelry applies for any jewelry that is for people 15 years or older. Therefore, we wanted to investigate kind of the discrepancy between those two categories and see if it would have any impact to our health and safety. Which led us to our research question. Can sweat take up any heavy metals known to be present in adult jewelry?
So how did we do it? So we took 3 samples from 3 price points from 3 businesses. The price points was important to us because of, as university students, fast fashion is a big thing. And so we got these necklaces that are priced within the range that most students will spend money on necklaces. Before testing, we made sure that these are clean of debris. We used soap and water and alcohol to make sure that there's been no oils that were transferred on from us before handling this. And then we created some samples before treatment was added. So like Ethan said, we produced a sweat solution. These necklaces were submerged for 4 hours. With our sweat solution, we consulted with other scientists as well that have done similar projects and just got some advice on like what compounds they were using, their reasoning behind things. And so we ended with using this recipe right here. This was from the International Organization for Standardization. So this had L-histidine monochloride monohydrate, sodium chloride, sodium dihydrogen orthophosphate dihydrate, grade 3 water, and sodium hydroxide. In a perfect world, we would have these chemicals and substances ready to use, but unfortunately, we had to make some adjustments. We were thankful enough that CLS was able to donate some, but we also were not able to get L-histidine. We consulted with one of the scientists and they have said that it's okay to leave that one out. And rather than the orthophosphate, we instead use potassium phosphate.
So like Mike said, we submerged the necklaces in the sweat solution for 4 hours. And what we wanted to look at before like kind of the sweat solution effects, we also wanted to look at what are these necklaces actually made of, what is their composition, because then we can kind of draw conclusions from that when we see if there was anything left over in our sweat solution afterwards. So this graph here shows all 3 necklaces and kind of their composition. So as you can see, there are peaks in 4 different points on the graph, and these correspond to the elements chromium, iron, nickel, and copper. So all 3 of our necklaces contained these 4 elements, and do align with some research that was done for necklaces and other jewelry from different countries, where they also contained high amounts of copper, iron, nickel, and chromium. So this showed us that we actually did choose 3 accurate kind of good samples for this project because they kind of represented a wide range of jewelry. And it was a good subset for that, and the low cost as well. We were able to see that just because they had a low cost, they still did align with the research and they still had the main elements that we might be looking for. This XRF scan is for the necklace 1, so our $10 necklace before and after treatment. So before treatment is the necklace before we submerge it in the sweat solution, and post-treatment is after. And we wanted to see, did the necklace lose any of its metal composition after it was submerged in the sweat solution from it being leached into the solution? And as you can see, the graphs quite closely aligned. Both lines really don't vary very much. If it is, it's just like by a tiny amount that was kind of negligible. And you can see that because of this, it really showed us that no metal composition from the necklaces really leached into our sweat solution, and it showed that it didn't really lose any of that composition. And now Oliver is going to talk about the sweat solution itself.
So we put the actual sweat solution after it had soaked, or after the necklaces had soaked in it for 4 hours, into the beamline. And when we first saw this, we were like, oh, awesome, we actually didn't find anything at all. That's really cool. So the argon presence right here is probably because there's air just around it as the beam is going through, and there's argon in the air. But if you're very astute to detail, we noticed later on that actually we did have very, very small lumps for 2 other elements right there, which was very exciting. The first one is so small, it is a very tiny little amount of iron. In fact, if we zoomed in close enough for it to look like an actual little peak, you would barely be able to see the graph at all. But it is there if you just squint a tiny little bit. But much more significantly, we were able to find copper. Uniquely, so necklace 2 was the necklace that had the most amount of copper out of all of them. It had like way more copper than the other 2 necklaces did. And we were able to find a very tiny amount of copper in the solution in necklace 2 had been soaking in for 4 hours. So this was really amazing for us because that means that we actually found a result, and you have no idea how excited we were. Yes.
So overall, our main takeaways from our science research was the metal composition of necklaces, and that aligned with prior research of having high presence of iron, copper, chromium, and nickel. And secondly, copper was seen to have some leaching into the alkaline sweat solution. And as we're going to shift a little bit from our learning on the beamline to more reflective thinking as educators of how we can, what we pulled from this experiment and how it's going to shape our future teaching. So our 2 main pedagogical points are through inquiry-based learning, students will learn transferable skills that will be applicable beyond the science field. And a growth mindset is inevitable when conducting inquiry, and as educators, we need to foster that and create an environment where students can develop that growth mindset. So first, we'll talk about some of those transferable skills. So like I said, this course is very, very unique, and we are working in a group of 4 for the entire 3 months. So navigating groups, group dynamics and collaboration was something we had to work on from the get-go. Group communication was a big part in that. We found what had to work for us. And this was very evident in the brainstorming process. We would meet inside of class and outside of class to discuss, and we ensured that all members felt as they were being heard. We were very, very cautious of considering all brainstorming ideas thoughtfully. And another part was ensuring that all members felt that we were playing to their strengths, and all members felt that they were positively contributing to our success. And another large part would be having a team focus and focusing on a collective success instead of the individual journey. We did have to shift our mindsets a little bit to focus on the team instead of just ourselves. And as we enter the classroom, this will be to help support the development of these transferable skills. A large part will be in modeling, active listening, and collaboration with our colleagues and also with our students. And also regarding group work, planning and organization is another one of those skills that were tested this semester. As for fourth year students, we have very, very busy schedules and we ran into many scheduling conflicts. And overall, we did have to make priorities and ultimately make sacrifices throughout the semester. And mainly this was seen in our beam time and our data analysis. We had to get very strategic and creative with our planning. Within beam time, on the day of, we were working individually in partners in a group of 4 and also dividing and conquering to ensure that all of our work would get done. And within our data analysis, something that worked best for us was booking study rooms and having late nights on campus and working together in person. So as we enter our classrooms and start designing our own inquiry projects, this experience gives us a great kind of guideline and will help us scaffold the inquiry process for students. And when they do get into planning or organizational difficulties, we'll be able to step in, give them direct tools, and help decide what scaffolding is needed for students to help them get back on track.
There's also some problem solving and adaptation that happened. So like we said, we had to substitute a couple of our substances and take away L-histidine. For our sweat solution, our pH was alkaline. Originally, the original sweat solution was supposed to have a more acidic pH around 5 to 7, and we ended up having an 11 for our pH, which was a pretty big change and shift. And rather than like having that like let us down, we had to like keep going and actually follow through with our experiment and stuff. And so that, like, as an educator, there's a lot of emphasis on perfection in science, and it sometimes results in students like either like steering away from like taking those like science classes, or maybe even like not feeling like they're good enough. And we want to really emphasize pulling students back, learn from like our experience, and also like share our experience with them about rather than getting perfection, learning from our mistakes, enjoying the process together, and the outcome. So yeah, like we want to have students like embrace the challenge and adapt to it. And like we've had multiple supports here, and so just modeling that with our students as well. Then data literacy and lab safety. So with data literacy, we aren't just doing labs, right? We want to start having students think as scientists. And so rather than just finding answers in like your assignments for that lab to do, really dig deep and look into like, hey, where's the why in this, and why are we doing this? How can I go and take this further? With lab procedures, there's a lot of attention to detail, and with the pH scale, an example of like hazard assessment and proper use. So these are a great emphasis on an example of scaffolding. So breaking down like complex tasks for our students and being able to create explicit instructions and modeling that again with our students. And then seeking help. That's one thing that for us we were very comfortable in doing, is seeking help with either Tracy, our instructor for our class, other scientists that have done similar experiments, other professors. We want to support our students and encourage them to do have their creativity in science, and with that, like, they need our support, and support is very important. Okay, so students with a growth mindset view ability as malleable and within their control, whereas students with a fixed mindset view ability as stable and beyond their control. So this is essentially something that we really focus on, is providing growth and learning from our mistakes, and we can talk more about that.
So that was kind of our second main takeaway in the pedagogy part of this project. So having a growth mindset means turning setbacks into comebacks. So initially, when we saw our results from the spectra, we didn't think that our results really helped us answer our initial question because of how little our information actually told us. We felt pretty discouraged, honestly, from like all the work we had put into the project, from like the preliminary work to actually spending time in the lab and then getting the spectra. It was pretty discouraging to find that out, but we had to kind of pivot our research focus, and we were able to kind of do that with help from Tracy. She would be asking us different questions about like how can we shift our mindset or change our questions that we might have had about the science to view our data differently. And also maybe look for sources of error. So like what could we have done differently, or what could we have done to change our results, or maybe ensure that they were more accurate. So from that, we were able to learn and reflect on our experience and find knowledge from it. And that's something we really want to emphasize with our students. In inquiry-based learning, the answer is not always super explicit, and they might not always be able to find that answer right away, even though some students really want to try to find that answer right away. They don't like having to put in a bunch of work or different mindset shifts to actually get there. So having this experience and being able to share that with them and kind of our journey would be one great way for us to encourage them to do the same. And further supporting future students and having that experience, we are also able to kind of just relate to the process of inquiry from start to finish to help and inspire our students in their own inquiry journey. So for example, one of the biggest challenges we had through our research that students of ours might also have in the future is just finding a topic or a research question that we really want to do, that really engages us, that really interests us, and something that can actually be pushed forward. So we are able to then share our own experience of how we did it. We went through a lot of brainstorming, a lot of different research, trying to figure out exactly what we wanted to do and how to narrow our research question down. And so yeah, being able to share that with students will be really helpful and kind of give them a different perspective. And also shifting students' mindsets away from failure and towards learning opportunities. So like I said, like reframing, how can you view your information that you got in a different light if it's not exactly what you initially thought? What could you have done differently? Asking new questions, and yeah, just dealing with maybe not explicitly having that answer right away. So this is kind of shifting gears a little bit, looking to more research. Like Mike mentioned, our pH for our sweat solution was not exactly what we were looking for due to the limitations of like the substitutions that we had to make, and also just the availability of different substances. It wasn't exactly what we were looking for. So we wanted to kind of look and see how could we have changed our sweat solution if we were to do this again. So we looked at some similar experiments. So in one study, this is kind of how they use the sweat solution. They submerged their jewelry for 1 week, whereas if you remember, we submerged ours just for 4 hours, and they were able to get more staggering results. They also kept it in an oven at a constant temperature of 30 degrees Celsius. We just kept ours out at room temperature as we were advised by a scientist that Janelle reached out to. They told us just keeping it out at room temperature would be fine. In another study, they submerged it for 24 hours, again, much longer than we did for ours, and they kept it at a constant temperature of 35 degrees Celsius. And the third study kept it at 36 degrees Celsius. And they did this because that's kind of the average human body temperature. So those are kind of things with time and temperature that we could have played with to maybe ensure better results for our sweat solution. And back to the limitations. So if you remember, this was our recipe, consisting of 4 ingredients and then some water as well. This recipe on the right is from a study that was conducted trying to find the most accurate artificial human sweat solution, and that is the recipe that they came up with. So this is just a zoom in on there, and these highlighted ingredients are the ones that we used. They ended up using a lot more ingredients, including some vitamins, minerals, some different metals, and just a lot of different ingredients that we didn't have access to, and also just given the limitations of the project and the timelines, we wouldn't have been able to do. However, with the resources that we had, we were able to kind of find the best way for us to do it. But if we were to do this again, potentially looking to see how could we work in some different ingredients to maybe make it a little more accurate and also balance that pH out as well. So from that, just in summary, we should maybe have submerged necklaces for longer than 4 hours, kept the necklaces at a constant temperature equivalent to human body temperature, and potentially used a different or adapted recipe to better simulate human sweat to create a more accurate pH. Now, bringing that kind of focus more into our future classrooms or as educators, we did a lot of research just for that and also like throughout our project. So we want to kind of bring forward the notion of the cycle of inquiry. And the cycle of inquiry is kind of, you start with a topic, you research, you do some work with it, maybe research throughout to answer some questions or any confusions you may have, but then also researching at the end too to kind of reflect and see what could you have done differently based on other people who did studies. We also want to bring forth the importance of relevant sources. This is another thing high school students especially might struggle with, is not just really always turning to something like Wikipedia for all of their information. So looking for sources that might have similar experiences to ours, contacting scientists like we did to kind of get advice from them. And then also evaluating and reading the research effectively. So asking students the question, will this research help your project given the circumstances or limitations? And maybe if not, what could you take from the text? So for example, with the sweat solution research where we showed that large recipe, a lot of the research was telling us about like, you know, all the ingredients they used, how they did it. And while we weren't able to relate to that, we were able to take away things like the time that they used or the temperature or those specific ingredients that they used and how they balanced the pH. So being able to kind of parse through a text and with the experiences that we had, I think we now have the tools to be able to show our own students how to do that.
So to summarize what we were able to find, the metal composition of the 3 necklaces that we used did line up with what you would expect from other research that's been done. And for our sweat solution, our necklace number 2, which had a whole bunch of copper in it, did leach some of that copper, a small amount, but it did happen, into the sweat solution. In terms of pedagogy, we found that there was a lot of transferable skills that we learned throughout this entire experience, including things like being able to analyze data, being able to go through research and collaborating with each other and some of the other people that we worked on this project with. And then the mindset shifts, we really see how this cultivates a growth mindset. You set out with this kind of inquiry project, not knowing what you're going to get. And so you have to be open to possibilities. And that was really amazing for us. So one thing that relates to all of our points throughout this presentation is inquiry. This is an inquiry project class. We think that we were able to see the perspectives of both the teacher and a student doing an inquiry project like this. We have a comprehensive view now of science and how it works and how to especially approach this in our own classroom. If we wanted to implement something like this, it might be hard for students to go through a project like this, not knowing what they're going to get and having to work with each other and potentially haven't done something like this. And supporting students is also hard if you yourself have not done a project like this. So we feel a lot more equipped now to support something like this in our own future classrooms.
And some people that we would like to acknowledge: Tracy Walker for patiently guiding our process throughout the semester, Tor Peterson for staying very late at CLS to help us with our scans, Miranda Vu for sourcing chemicals for our sweat solution, and Tim Molnar for trying to find us some colors. Here are our references here that we use. That's it. Yeah, thank you.
Yeah.
Yes.
So you talked about the pH of your solution, and I'm just wondering if you did any investigating as to what you'd expect you had the right pH versus the pH you had, like how might that change your results?
Yeah, I think that based on some of the research that we looked at, that's partly why we did this research afterwards. A lot of them used acidic solutions, and they also found like most of the research that's been done about this has found that metals do leach, like all kinds of metals do leach into sweat solutions. And whether that's strictly due to the fact that it's acidic or not, because there are a lot of other things that they've done, like agitating it or temperature as well that they looked at. But we might expect to see something else like that, yeah.
I was a couple minutes late, but I maybe missed your hypothesis of the right question was, but one aspect that I failed to see here was you determined that there was copper and iron and stuff, but one of the most important things, what's it mean? Like you never said anything about meaning, is it going to affect human health or anything? But why did you do that? I don't know if your whole project was just to determine whether there was metals, but maybe there should also be a reason. Or another reason for doing it, like is there a human aspect to it or something?
Our project was specifically to determine whether or not metals leach. We didn't have anything to look at health aspects of it, but if things like copper or iron leach, then that might mean that things like lead or cadmium also leach, which are known to have health effects. But that wasn't, we didn't look at health effects in our project.
I know, just whether comment whether
Yeah.
it was or copper.
I do think that that would be an important thing for like future study. If we were to do like some other kind of project related to this, it would be really interesting to look at whether it does affect your health or not.
Okay, great job, guys. Thank you. And the next presentation will start at 1:45. We'll have a bit of a pause between now and then. Can you mute? Wait, I should be able to do that. share it on there.
Well, that worked.
All right, thank you, everybody online, for your patience while we dealt with some technical issues. Thank you very much, Connor, for supporting us.
So do you want me to stop sharing this one?
No, that's what you're seeing on there.
Yeah.
That's the Zoom thing right there.
Okay, but we won't be able to change it from there.
No, so you'll just have to look at me and I will advance your slide for you.
Sure, okay, beautiful.
Okay.
I gotcha. Yeah, I gotcha. You guys got this. Okay, again. Thank you for your patience, everybody. My apologies. Are you guys good?
Yep.
Okay, you got this.
Oh gosh, you guys all had to come in for our presentation, I see. Good morning, welcome to our lovely ECUR 411 presentation. My name is Madison.
I'm Allison.
I'm Brandon.
I'm Mita.
And so we are a group of education students learning about inquiry-based learning. But we really believe that in order to be able to teach it in the future, that we had to fully put ourselves into this experience and actually have a strong understanding of it. Previously we have read lots in classes about inquiry, but have never really experienced it ourselves. So this was a really neat project and an opportunity for us. So we all started with a shared curiosity about food and the environment, which really led us to our research question. And we really wanted to take this opportunity to work through the inquiry process the same way that we hoped our future students would. So first by questioning, then collecting data, following the evidence, and then allowing their thinking to change over time. So, as you know, we are the team. Sorry.
Sorry, I was writing in your notes.
So why did we choose flour as something to research? So we chose flour because wheat is consumed by millions of people around the world daily. But have you actually ever stopped to ask yourself what is in flour? What are the nutrients that it actually contains? Anyone? Maybe a couple. Other than that, like no one. Yeah, neither did we. So this is where our true inquiry really began. So we stopped and actually started questioning our everyday assumptions and tried to see, is this actually a safe food for us to eat? So we did approach this project using two-eyed seeing, which is a concept by Elder Albert Marshall, where we use our one eye for Western scientific methods and the other eye for understanding the broader meaning and connections to people and the environment. So for us, this was never just a science experiment, but it was rather a way to learn about how everything is connected. And so like students in the classroom, we built our question around something we already knew. We previously knew that arsenic has been a known issue in some crops such as rice. And so we wondered if the same pattern may be taken up in wheat. And so this was a key part of our inquiry because this took us a long time to build our question. And we built our question from previous knowledge.
Okay, so like Madison said, we knew a little bit about the potential problems of arsenic contamination in crops. After doing a little bit of background research, we found that there was lots and lots of research on arsenic contamination in rice. And also there was research for wheat crops, but it was a little bit disproportionate, and we wanted to know why. And one of the reasons why is that, as you can see in these pictures, the one on the left is a rice crop, and the one on the right is a wheat crop. The rice is obviously flooded, which is, as many of you probably know, that's a common practice. Rice crops, are typically flooded during the growing season, but wheat crops aren't. And so the effect that has, if your water is contaminated with arsenic, it is a lot more likely for that arsenic to be taken up in the rice. It's a little bit harder in wheat crops, but it does still happen. Another thing we discovered through our research is that arsenic is what's known as a non-threshold level carcinogen. So essentially what that means is arsenic can have carcinogenic effects on your body if you're ingesting certain amounts of it. But there's essentially no agreed upon safe level of arsenic. So if you're ingesting any amount of it, it could have harmful effects on your health. That's kind of why we were interested in looking into this. Go to the next slide. So another thing that we kind of wanted to compare is the white flour versus the whole wheat flour. After doing a little bit of research, we found out that whole wheat flour tended to, if it was contaminated with arsenic, it tended to contain a bit more than the white flour. And the reasoning that they found for that was that the bran of the wheat kernel, as you can see in this lovely diagram, tended to take up arsenic a lot more than the endosperm. And so white flour only contains the endosperm of the wheat kernel, but whole wheat flour contains the endosperm, the bran, and the germ. And that had implications for our hypothesis later. So, what was our hypothesis? So we wanted to look at flour, not just from Canada, but from different areas across the globe. So we wanted to look at North American flour, flour from Europe, and flour from Asia. So we chose some flours from Canada, the US, Italy, and India. We tried to get whole wheat and white flours from all of these places. You'll see later it was a little bit of a challenge, but we did our best. And part of our hypothesis was that since we knew that their arsenic contamination happened more prevalently in the South Asian countries like India, we predicted that we might see more arsenic uptake in the wheat that was grown in India compared to the wheat that we got from Italy and North America. And then the second half of our hypothesis, like I talked about a minute ago, was that we expected to see a little bit more arsenic in our whole wheat flour compared to our white flours.
Okay, so how do we actually test this? So this is when we really brought in our Western eye, so that our Western scientific eye, sorry, so that we could really actually test and collect our data here. So as you can see in the middle, we have our little sample tray. And what we did was first, obviously wipe down everything, and we set up 2 different stations because half of us were working with one flour and the other half of us was working with the other one. And we didn't want anything to get cross-contaminated. So we made sure we were working in separate stations during that. And so we filled up our sample tray and leveled it out. We did not weigh the flour at all. We just kind of did this based on volume rather than mass. And so one thing we did notice was when putting the tape over, it was the whole wheat flour that was more static, and it actually was a lot finer. We had tested some of these flours at home previously, trying to decide if we wanted to do a paste or not, and we didn't get the chance to actually test the whole wheat one. So this was really interesting when we were actually in the lab. Yeah.
Excellent. Yeah. And this might be a good time to actually explain the tool that we use to collect our data. For those of you who aren't aware, we were able to use the synchrotron, a very unique experience. And the specific beamline we used was the IDEAS beamline. This beamline uses X-ray light that slams, I guess, out of a photon gun, you could think of it, into our samples that then emit X-ray emissions at specific energy levels that the beamline is able to collect and then give back to us in the form of an X-ray spectra, which is just a fancy term for a graph. The scientists will definitely use the term spectra, but we can use graph for this. Yeah, it's a lot more complicated than that, but the specifics are that's all you need to know. You can put the next slide then. This is me. Okay, sure. Yeah, so after we got done with the samples, we were able to pull them up onto a screen. This is where we were able to start seeing our data collection for the first time. As we'll get into a bit later, our results were far from what we expected, but this procedure was really cool. It was my first experience really actually getting into the inquiry. We had done a lot of research, a lot of preparation, and to see it paid off in a very expensive, very unique laboratory was pretty amazing. Yeah.
Yeah, and it was, we collected our data, and so that's the yellow pieces there that we put into the room where the beam line was, and it's a concrete room, and the radiation wouldn't emit out to the rest of the public, that like the rest of us students. And so this is like a totally different room that we were all sitting in, and we were all amazed with at awe and looking at all the screens and everything coming up. So us using our two-eyed seeing, my little First Nations eye on the other side was all amazed. So it was a beautiful experience, and I commend like our staff and our teachers for letting us come into the building to, you know, really enjoy ourselves being, I don't know, it felt like being little kids again, like learning and just all brand new stuff. So yeah.
So now we can actually get into the X-ray spectra. XRF stands for X-ray fluorescence spectra. Up at the top, we have a legend for you to see. Hopefully you can see it okay in the back. These are all the different types of flower that we were able to test. We tested much more than this, but to keep it easy for you guys, we just simplified down to one from each flower. On the horizontal line, we have different energy levels. And as the last group stated, elements release emissions at a certain energy level. So using this graph, we, and the help from Tracy and Tor, we were able to figure out which elements are which. And we have them lined up here in beautiful colors for you guys to see. And on our vertical, our y-axis is the photon count. This is how many photons were absorbed after the emission. So this kind of gives you a relative concentration. You can't say for sure what the concentration is, as it's purely just photons being released from the elements, but we can use it to gather relative information. So now we are going to zoom into 3 different elements that we thought were kind of interesting in our graph. You can go to the next slide. The first one being arsenic. The previous group, their X-ray graphs were somewhere between 10,000 to 100,000. As you can see on the left, our photon counts for arsenic barely peaked above 50. So if you're worried that there's a lot of arsenic in your flower, don't worry, there isn't. Specifically, one thing that we thought was interesting when we were going through this is it was only the white flower that had any presence above 0 whatsoever. This was the complete opposite of our hypothesis, but this isn't concrete, as the very fine consistency of our white flower might have scattered the light differently while the sample was being analyzed, giving us a potential source of error. So it's not to say that the whole wheat didn't have arsenic in it, it's just that the X-ray light might not have scattered enough as the white flower did for us to see it. We can move on to the next one, which is zinc. The general trend, again, we can see our white flowers are down at the bottom here. We expected this as most of the minerals are taken out of the germ and the bran. But one interesting thing that we noticed was the highest photon count of around 1250 was actually our Indian white flour. This is not what we expected. We thought that all the white flours would be relatively similar, with the whole wheat flour actually being higher. But yeah, the whole wheat did show some presence above white flour, but generally we were very surprised to see that the Indian white was the highest. So we go to the next one. And we saw similar results with our iron concentration, with peaks of around 1,000 for our Indian white flour once again. This was the same trend of white flour being the lowest in North American and European countries, with whole wheat being in the middle. Overall, these were the three elements that we were really surprised by, and we were hoping to see different results, but we had to shift our focus, and this is what we ended up with. So
Yeah, it was really cool. Our inquiry really changed at this point, because as we sat in the other room getting our results, we went, oh, there's not a whole lot of arsenic. I mean, that's a good thing. But then we're like, well, now what? And that's when we all of a sudden started seeing the high levels of the iron and the high levels of the zinc. And that's when we really started to switch our focus, because it so much wasn't about proving our hypothesis anymore. It was about, what did we see? What can we go? How can we go from there? Why did we see the results that we did? So this is a lovely little comparison chart about what our initial hypothesis was. And as you can see, the data actually showed very little arsenic, but iron and zinc were all presented in very high levels, which we actually didn't expect.
yeah, so we had to, our expectations were clear. We had done previous research that indicated our hypothesis had some merit. But instead of trying to force our hypothesis with our data, we just followed the evidence and shifted our focus into a new light, which I also will talk about now. Slide.
Next slide. Okay. So we have to ask the question, why are there high levels of zinc and iron that we're finding in flour? And the reason is biofortification. So as it says here, wheat makes up about 20% of global caloric intake. The main reason for that is it's grown worldwide. It's easily accessible to most people in most places. And so something that's not easily accessible in the case of iron, for example, is red meat. So if you're not getting enough iron in your body from red meat, it might be a good idea to fortify your flour with iron so that your citizens can stay healthy with this more accessible food source. Go to the next slide. So one ailment that this biofortification is trying to combat is iron deficiency anemia. So according to the World Health Organization, anemia impacts about a quarter of the world's population, and iron deficiency anemia specifically is the most common form of anemia. So what's happening in your body when you have anemia, if you don't know, you don't have enough iron, obviously. If you don't have enough iron, your red blood cells can't make hemoglobin properly, and then your red blood cells won't be able to transport and carry oxygen through your body, which is very, very bad. And this can lead to side effects like tiredness, weakness, cold hands and feet, just other negative consequences. And so, like we talked about before, fortifying flour, which is an accessible resource with iron, is a good idea to try and combat this.
And zinc deficiency, well, we don't see it largely in North America or Europe because our diets are much different than South Asia. It is actually a very prevalent issue within South Asian countries. Up to 30% of Indian citizens actually face zinc deficiency at some point in their life. That's from Akatar's study in 2013. Zinc is a necessary mineral. Zinc is a necessary mineral for our body in various different systems. The largest symptom that will often occur first is a weakened immune system. So you're going to get very frequent colds, and if you get a cut or a bruise, it's going to have very weakened healing abilities. Other symptoms with increased zinc deficiency and long-term zinc deficiency is loss of appetite, as well as alopecia or hair loss. Again, we don't see this very much in North America and Europe. In South Asia, their diet includes a lot of nuts and phallic diets that inhibit zinc absorption through the body. So they require zinc biofortification much more than we do in North America and Europe.
So as you can see, just as Brandon was explaining, in Canada, all our food must abide by regulations set out by Health Canada. And so it is actually mandatory for iron to be added back into white flour after it has gone through the bleaching process. However, you don't see zinc. So in Canada, because it's not really an issue in Canada, they don't have to put zinc back in. They can if they choose to, but then they must put it on the label. But in the South Asian countries, they have to, it is actually mandatory for them to include it back in because it is such an issue in the other countries.
And Ricky, it's my turn to talk now. Okay, so we connected to the two-eyed seeing pedagogy, and it's a teaching from Albert Marshall, which means learning to see with both Western science and Indigenous knowledge. With the two-eyed seeing, all this research that we did would just be all numbers and graphs and us not understanding what's going on with the human and cultural meaning behind what it is. So in our project, it helped us connect and understand the data while Indigenous knowledge is helping us reflect on meaning behind it, especially how food connects us to health, land, and community. The flour is not a traditional food source for Indigenous peoples across the world in places like Canada and India. The colonization changed traditional diets by introducing processed foods like flour, sugar, and other packaged goods. Indigenous peoples were often moved away from their traditional hunting lands and their collecting of herbs and berries, and had a limited access to their original food sources, which forced them to shift their eating habits. Over time, the diet has changed and linked the higher rates of health issues such as type 2 diabetes. This helped us realize our experiment is not just about science, but also it's about lasting impacts of colonization on Indigenous health and food systems. The two-eyed seeing pedagogy reminds us that everything is interconnected: water, air, environment, our soil, wheat, flour, and us, the consumers, human beings. And the health is being understood as everything is one system and not separate parts. So everything needs to be looked at as one. As future teachers, we can bring this into our classrooms by connecting science to real life culture, community, and to help students seeing the learning as being meaningful, inclusive, and connecting to the world around us.
Okay, so inquiry is not just about proving a hypothesis. So when we started this, we are going to determine whether flour has arsenic in it or not. That was kind of how we came into this. And as we actually started doing the inquiry process and the project, we're like, yeah, so we actually need to shift our mindset, because it's not about proving that there is or is not arsenic in flour, but let's find out what's actually in flour and let's go from there. So again, inquiry is the process of questioning, collecting your data, and then allowing the evidence to guide you rather than you guiding the evidence. So by approaching this project using two-eyed seeing, we were able to deepen our scientific understanding and our Indigenous connections, understanding that we are all one system and not separate parts. So as Nita was saying, that we are all interconnected, the soil, the wheat, the flour, us, like everything is interconnected. So it's really important to understand what nutrients are in our food that we grow and how that is affecting us daily. Thanks.
Yes, sir.
You mentioned before that the difference between arsenic concentration in the whole wheat and the white flour was due to some fluorescence. It's just really a dilution effect. I think the endosperm, if you assume that there's 1 unit of arsenic, the germ and the bread have 0. Well, when you have whole wheat flour, it's going to be half the concentration if you assume that. So we just go below our detection. That's why you don't see it. It has to do with fluorescence, sure. You're not going to make fluorescence photon. That's the reason why you're seeing a difference in whole wheat and
That's really interesting. Yeah, we were kind of wondering why there was such a difference, but that makes a lot of sense now.
Was there a question or just? With that,
No,
okay.
it was a comment.
So, you talked about getting flour from different countries.
Yes.
Do you know where the wheat came from to make it?
Okay, so that's actually a wonderful question, because we contacted everybody that we could to try and figure out which regions the wheat came from. So when I was on the phone talking to someone from Canada, they had tried really hard to pinpoint exactly where it came from, but they couldn't exactly tell us where it comes from, because they collect their wheat from mainly Saskatchewan, Alberta, and Manitoba, they said. So most likely in Canada, the wheat would be around there. And then Brandon, you can tell them about your lovely response you got.
We tried to contact the Italian company. It looked good. They have specific batch numbers and dates that the flour was milled. So it seems like they have the information to be able to tell us, but bureaucracy kind of got in the way, and we just ended up getting a lot of very obvious AI ChatGPT responses from the company. So it's, as far as we can tell, grown. They have 2 major sources, Naples, Italy, as well as a northern region in Italy. I can't remember the name. But it seemed like they might also source from other nearby European countries, so we couldn't say for sure exactly where it was from, unfortunately.
Okay, so the reason I asked the question is I used to live in the south of Italy, and if you ever buy Barilla pasta, get this out with me, get it here, that's actually made from Italian flour, but the wheat comes from Saskatchewan.
Oh.
So it's entirely possible if you're looking at Italian flour, you're actually looking at exactly the same flour.
And so is it milled in Italy? Like, is it grown here and then shipped there, or is it just?
The rules for Italian flour are very, very strict. There's flour makes pasta.
Yeah.
So there are rules about what kind of wheat you can use to make flour for pasta and how you mill it. And to be called Italian pasta, it has to be from wheat that's milled in Italy, but there's no rules about where you can get the wheat from. Historically, Italy is a terrible place to try and grow wheat. Even back in Roman times, they got their wheat from North Africa. Okay? So they've always been looking for sources of wheat outside Italy. And, you know, you think about this concept of everything is linked, the idea that you take wheat, you take it in a bulk container, you put it on a ship in the Seychelles, you send it through the Mediterranean to Bari, it gets turned into pasta, which gets put in a container and goes all the way back to the
Yeah.
Oh, maybe that's why we got really chatty responses.
But it's not even just kindness, it's not, it's the kind of week, it's the week that we're spending at our German meet from southern Saskatchewan, so there's the pasta. So even effectively, everybody give an example, German wheat grown on, different species of German wheat grown on the same soil. One was shown to accumulate high cadmium concentration, the other was low. So BCH, so your comparison of whole wheat and white flour, there's so many variables that you haven't considered,
Okay, thank you. I'm going to call this now to let the final group get themselves set up, just in case we run into something. Okay, so online, thank you. I'm going to probably mute us again so that you don't have to listen to us while we figure this out. There you go. Okay. So we should be rolling. And look at that. We've hit our time mark again. Look at us roll. Okay. Thanks to those of you that have stuck with us for the majority of this time. That's beautiful. I really, really appreciate it. Bring us home, guys.
All right. So, yeah. Hi, everybody. This is our presentation. We are the Rad Nugs group. We're dramatic. All right.
So I'm Alana. In true ed fashion, we are going to share a fun fact about ourselves. So I am forklift certified.
My name is Delaney Humphreys. I was a welder for 4 years before joining ed.
I'm Connor Taves. I am also forklift certified.
I'm Sasha. I like to attend Canadian Burning Man events, and when I do, I go by the moniker the Lizard King.
It works. Okay, so our main goals are kind of points in this presentation. We're going to talk about what we found given our investigation of chicken nuggets. We're going to talk about why chicken nuggets are crispy, and we're going to look at the difference in nutrient makeup of different types of chicken nuggets on the science side.
We are also going to look at our pedagogies of teamwork, curiosity, and inquiry, and why humor is very important in inquiry.
All right, so how did we get here? I'm gonna take us back to the very start of our semester. Tracy's introducing this whole project, and I was pondering why I did not read the syllabus before I attended class. And she's like, all right, you gotta come up with this project, and you're gonna do inquiry, it's gonna be amazing. And the whole time I was just sitting there going, I could really go for a chicken nugget right now. So I turned to Delaney, and I was like, hear me out. Chicken nuggets. She was like, yeah, absolutely. Come on, let's do this. So we looked around the room and we were like, oh dang, we gotta get somebody else in on this. So we landed on Connor. And we, class ends, we're walking out. So we cornered him outside of the education building. Said 2 words, chicken nuggets. He was in. So now we've got 3. And we were like, we're not fully rounded. We need one more addition. So Sasha joins. We were like, all right, if you're enjoying this though, we're going in with humor. It's a chicken nugget. Let's see what we can find out. And our team was complete.
So the idea was there. The idea of a chicken nugget and putting it in a synchrotron is patently absurd, but also something that, we were committing to the bit at that point. We were all the way in. And so we had a few questions. And we wanted to really narrow down a hypothesis and make something that, ask a question that the synchrotron could answer in some respect. So our first and most broad idea was, well, what's the best chicken nugget? Because we're still thinking in ed brains, and we're thinking in 4th year university student brains who have to hit up McDonald's after we come back from class sometimes. So sometimes that's what it is. So what's the best chicken nugget? Now, that was ultimately too broad, and that best is subjective. We have too many variables, not gonna work. Oh, we got a killer delay on here. All right. Next, we talked about, okay, so let's limit our scope a little bit. What is the crispiest fast food chicken nugget? We're looking at fast food that's going to be a little bit more accessible. It's going to be easier to actually consider our variables. We won't need to make anything or, fry in the lab. So that'll be a lot easier. And so what is the crispiest fast food chicken nugget? And we needed to even limit that down a little bit and kind of define our terms. And we'll go into that a little bit later, but we narrowed it down to 3 chicken nuggets, and we wanted to compare basically the structural differences and why and how that correlates with a better crunch. So when you bite into one chicken nugget from one fast food restaurant and you bite into another, why is one crunchier than another? Why is this one better, so to speak. Crispiness is one factor, flavor is another. We can't exactly test flavor on synchrotron. So we kind of limited that, our second one down, and that was kind of what we landed on. But, come on, but, there we go. We, at that time, only were working on IDEAS, and IDEAS is mainly suited to focusing on the chemistry side of things and looking at the makeup of the chicken nugget. But we were talking more about imaging. We wanted to look more at the structure of breading and what's inside breading and different levels of pores and sizes and that kind of thing. And so we didn't know if we were going to get access to another beamline that we would be able to do that on. And so we kind of changed focus a little bit. What we did was then looked at the difference between nutrient content of emulsified and whole muscle chicken nuggets. So if you go to somewhere, and as my legal counsel, Tracy Walker, has warned me, I can't say where we got our chicken nuggets, but somewhere like a Wendy's or a McDonald's, you go get a chicken nugget there, and it's not really, like, it's meat, but it's the way the meat is sourced is they take large chunks of chicken and they grind it up and they emulsify it with other chemicals, and it goes into this pasty goop thing that eventually gets fried. They were known as goop nuggets colloquially between our group. And so we were wondering if those nuggets would have different nutrient makeups or nutrient values than something like a whole muscle that would just be generally cut up chicken breast or something like that, that would, you know, it's a little more natural, so to speak. It's whole muscle, and we were wondering if that would ultimately change sort of value that we saw. And so that's what we tested on IDEAS. Now, we've talked a little bit, we've heard from a couple other groups what IDEAS is, and so this is the imaging that we could actually do on IDEAS. This is our chemical imaging. Where's my stick? There's my stick. I feel a lot more scientific now. And so on these are basically scans of a section of the nugget, and it's looking at the chemical makeup of that piece of nugget, looking specifically at one element. So in this case, it's our iron, and we have like a small piece of iron there, or a small concentration of iron, but generally there's low density in other areas. And so this doesn't tell us anything about texture, this doesn't tell us anything about structure, but it did tell us a bit about that second question. This is what we could get off of BMIT, which we were very lucky to get some time on right at the end of the shutdown. And what we could look at here is this is part of the breading. We'll look at a bit more of it later, but just as an example to get the idea of what we were able to use that for. BMIT is our biomedical imaging beamline, and so this gives us actual x-rays the same way you could x-ray a broken arm, but chicken nuggets. And so this is what we're able to look at using BMIT.
Thanks, Doug. So, really, in a sense, our chemical analysis are like our most interesting results, right? The thing that we were really excited about was kind of BMIT scans, creating a 3D model of the nugget. So I'm really here to kind of whet your appetite for kind of the crunchier results that Connor's going to show us later. So first, here is a chemical analysis of our breading. Now, the things that we kind of expected to see, we did expect to see a lot in our breading samples. And we kind of figured that we would see kind of higher concentrations of like iron and zinc, especially in like our meat samples, like in the meat as we scanned it. So here we have our breading. We see pretty large concentration of iron. We see smaller concentrations of zinc, except in the case of nugget A, where we see a larger concentration of zinc. But as our next slide shows, maybe I should come over and do that. Thank you, Connor. The thing that surprised us when we were doing this is we actually saw higher concentrations, like in a lot of cases, significantly higher concentrations of iron in our breading rather than in our meat. We suspect that's probably because of the iron biopurification the previous group talked about in the wheat. But as you see here, because we can see like in the meat, nugget C with the exception to this, where we actually see kind of quite high concentrations of iron. as opposed to in their breading, which is right here. Actually, we see pretty high concentration of both. But for example, in nugget A, we have like very low iron in the meat, whereas in the breading, we see a significant peak. But all of this led us to quite a surprising result. Yes. So this is a spike of titanium in our nugget C. So in our, now unfortunately, as Connor pointed out, I'm not allowed to tell you where you should not be buying your chicken nuggets, but it was in a multiplied recipe. And this was when we were sitting sort of in the beamline, and it came in and it was like kind of a whoa result, right? Where we see that spike, we're like, whoa, what is that? So we speculated a bit. We know that titanium dioxide is often used as a whitener in recipes. The company that produces this particular nugget claims they do not use titanium dioxide as a whitener, but even so, that was something we found. So because of this spike and sort of like the excitement around it, that's the nugget that we chose to do our chemical imaging on. So now, and to be clear, this was a scan that we did in the top left quadrant of the nugget, or of our nugget sample, from what I recall. So we didn't see that spike in like, because we did several scans of the nugget, and we didn't see that in every part. Just in one scan, we saw this big titanium spike. And so, like I say, we have our different elements here. As Connor pointed out earlier, we have our iron here. This is our copper. This is our zinc, and this is our titanium, right? Where you see this big old red splotch, which is our significant titanium concentration. Here's a zoom in, because again, it was a big result for us, so we wanted to give you the big presentation of it. Big concentration, real dark right here.
So, I don't need this script, you know. Really, what this was like a whoa moment. And it kind of like brought all of us a little bit of like a hurrah moment that we actually found something. Through this experience, really what we learned was working as a team is really hard. We are all coming from very different backgrounds. We all are very busy people. We got people working full-time jobs on top of school. We're all fourth years. Lots of stuff going on. Trying to schedule around that is a nightmare and led to a lot of inconvenient meetings, people taking on parts when they couldn't be involved in other things, and really just trying to divide up that work. And that kind of taught us, like, because when you're working with little kids, you're like, oh, why can't we just work together? Like, but then we were like, oh, shoot, we're kind of adults, and this is hard. So it kind of gave us a little perspective and a little bit of grace when we're doing this in future projects with our students. And really what happened is we figured out we had to break this down. We had to take out different parts. We had to divide and conquer. And really that helped us bring the project together and kind of see how that would happen in a classroom setting.
Before we move on, to be very clear, this was taken in the hallway immediately before entering the lab. We were very scrupulous about our PPE use when we were in the lab.
Okay, so why is curiosity important to inquiry? So what we discovered was us being curious about what we're learning about drives our learning process. If you don't care about what you're learning about, you're not going to want to keep learning about it. Fair. And then it encourages questioning. There was a lot of times where there was a lot of random questions about what a nugget really means. And that just keeps our brains going through. It also promotes engagement. We were all super involved in this because it involves chicken nuggets. And that's just a fantastic way to do something in your fourth year. And it provides deeper understanding. So when we are able to ask questions, be curious about what we're learning about. And we're like, I finally understand what a good nugget really could mean to me and how it changed my life. So I found this article. Learning benefits of secondary school students' inquiry-related curiosity. So, same thing works for students. And being curious about your inquiry leads to meaningful learning. If they care about it, they really, really care about it. Oh, and it also leads to their building inquiry skills. If you start a child young with something that they are curious about in inquiry, they will keep doing that. for their whole career. And it also leads to skills that develop over time, like group work, which I wish we all had better sense of that going into this, but we built a great team.
So overall, what we found was that we were using a lot of different learning approaches. In education, they give you so many different things you can try. And really what we were able to see is that inquiry learning is present in so many different styles. We were looking at what we were doing and we were like, we're doing so many different approaches all within this one little project. So we talked a lot about experiential learning. So what experiential learning is learning through doing. So you're doing it, you don't know what the outcome is going to be, and that's okay. That kind of experiential, you don't know what's going to happen, and then you reflect on it in the end. That happened so much in our process. Yeah, and it was just like a really great way to actually take about what we're hearing in class and applying it. Experiential learning is super cool, and it was great to just get to be hands-on and actually experiencing learning. When Tracy pitched this project to us, I was like, God, I don't know. But when I was actually hands-on and being part of it, it all started to click in my head and I could kind of follow along, which was a big win on my part. Really what we were doing was student-centered learning. We got to pick our topic. We kind of dove in on what we were interested in. We were all giving ideas. We had so many different pitches of where this could go. Chicken nuggets is such a broad category that could go in so many ways that so many people know things about and have opinions about. Of their favorite places. So really what we were doing is taking ownership of our learning. Where do we want to take this? What do we want to do? And really what we had is we had a teacher as a guide. She really guided us through the process. She didn't tell us step by step what we had to do. We were able to take control of that, and really that's what we want to do in our classrooms. What this is active learning. So we didn't just listen to Tracy tell us about the synchrotron. We actually got to step in and use it, which meant way more to all of us and was way more authentic on students. Authentic experience. There we go. So yeah, all that is, it really improved our understanding and it really gave us a picture of when we're in the classroom, instead of just reading that textbook, really the difference of how much you take away from that experience.
Well, hilarious topic. Organic chicken nuggets. Funny. So, with humor and inquiry, it creates a safe learning environment. If this was super serious and like medical, it wouldn't be safe for me to like say throw a chicken nugget at Connor. I couldn't throw like a limb at him. So it also encourages risk taking. So we were able to make jokes and try different things because no one's life is on the line with chicken nuggets other than the chicken baby. So it also encouraged engagement. We were also engaged in this topic. I went and got chicken nuggets yesterday after school and texted Lana and I was like, this is great. Now I know everything about what's in this and I might not be happy about eating it. The creativity side of it. Beautiful side of creative art. And it reduces stress. I don't think I was very stressed during this process. At all, really. Other than when I'm in the lab and I'm holding my hands like this so I don't touch it. I also found this article, the use of humor during collaborative inquiry. This is an image of me on ChatGPT. Please read it. It's from Iraq. So for students, when they are having fun and laughing, it can help build a group connection. The students will be able to come together and laugh with each other rather than having a very serious conversation. This works especially well with younger kids. I like grades 5 to 7, and they think it's hilarious when you give them any opportunity. And it also helps them to handle frustration. If it's funny, it's easier to get over that frustration of something not working because there's so many different routes you can take. And it also helps to share ideas and keep inquiry moving. Students are able to share ideas with each other, keep inquiry moving, talking about different aspects of everything, and have fun and laugh about it. And I know they're not being lab safe and beamline safe, but that's okay.
There's a chicken.
So what we really got to take away from this is just having skill built in this process. We did so much critical thinking, we got to analyze all the results, taking this huge thing and really just getting to break it down into everything that we took away. We made awesome connections, like I know so many things about these people, and they were just like strangers and we passed by in the hallway and now we're like friends and doing things. And we really did a lot of problem solving. We had problems with movement in some of our scans. We had the problem that you could only buy chicken nuggets after 11 a.m. And they're very stickly about that. I tried to go at 10:58. No go. They sent me around. I had to wait 2 minutes. Very stickler on that. All these little things that we didn't consider. That we really were like, okay, now we got to pivot and thinking we can get around this. Communication. Our communication at the start was rough, but really as the process went, we kind of figured our groove. We really developed our bonds and we figured out our best ways to communicate, who works with this way, who works that way, all that kind of thing. And then really we just got to be creative. When we approached this, it was like, what is a topic that isn't super intimidating? This kind of project is huge, and when you're thinking about the aspect of our learners, how intimidating that first thought can be. So when we got to pick our topic and pick something that we got to be creative in, it really made it way less intimidating to approach. And that's kind of something we can take into our classrooms.
All right. Uh-oh, I broke it. Oh, we're back. So as a little bit of pre-research on the idea of looking at kind of crispiness in a nugget, obviously there's, you know, some level of observation we can do to look at that, but ultimately crispiness is a subjective and a culinary term effectively, where there you can measure acoustics, you can measure small things like that, but generally crispiness is going to be which one feels better in your mouth, which one, when you bite down, is going to have the best crunch, so to speak. And because of that, we needed some actual survey. So we did a little bit of delicious anecdotal research between our group. We also got a survey group to test our 3 nuggets. And of these 3, so sample C was one of our emulsified nuggets, that was the titanium one. Sample B was also a not titanium, was an emulsified nugget. And sample A was a whole meat, whole muscle nugget. And these were our results. So sample C and sample B were rated fairly similarly. And sample A, which we'll take a look at in a little bit, had a decently higher rating just due to the, I think, the structure and the techniques of the breading that were used. So what makes fried food crispy? I went on a bit of a rabbit hole on this. So it's like 11 o'clock at a Tuesday night. But I found several papers that I found very interesting. But ultimately, there are 2 kinds of crispiness, if you will. And that is your wet crisp and your dry crisp. Now, if you eat something like an apple, that's going to be crispy, but it's not fried, right? And so that's kind of a question that, why does that happen if it's not fried, if only fried food is crispy? And so the idea behind that is when you bite into an apple, you are puncturing the cells, and those cells are filled with water. So those plant cells, you bite down and you puncture them, and the crisp is released by those cells rupturing and kind of exploding into your tooth. And your tooth feels that, the nerves in there, and that sends a signal to your brain. Now that's kind of your wet crunch. In your dry crunch, which is a little bit more intuitive, if you think of like a potato chip, where that's fried and it's also used, or it's also crispy, but it's not wet. And if anytime a potato chip gets wet, obviously the greasy ones at the bottom of the bag, those aren't exactly crispy. And so the crisp happens with that potato chip is when you bite down into the air-filled pockets of that chip. What's going to happen is you're going to pressure and pressure and pressure into those pockets until they eventually burst. And what happens is the frequency that the surrounding chip or the surrounding pockets make when they snap back into place after bend, and some of them will crush, and the surrounding ones will snap back, and that snap back is what's going to give you your dry crisp, so to speak. And so that is what causes those textural sensations when you bite into a chicken nugget. Now, in this case, chicken nuggets have both wet crisp and dry crisp. And I think those are very important because without the oil, that gives a nugget its wet crisp, you are going to be missing a significant amount of textural sensation. So when you bite into a chicken nugget, you're experiencing the dry crisp of the breadcrumbs, the fried breadcrumbs, which have had their water evaporated due to hot oil, but you're also experiencing the wet crisp of biting into those more saturated pockets of the nugget that you will experience that are filled with oil. And so we kind of looked at both when we were going into this.
Before you move on, during our preliminary research, we found a guy named Michael Naughton, and his whole shtick is deep fried food. All of his research papers, all of his inquiry projects, everything he does is around batter and deep fried food. If you have the chance to look him up, highly recommend it. Amazing research.
Is very helpful to this.
He was super helpful to us figuring out our main question. But another thing is, he made us feel like our chicken nugget inquiry was not as silly as it could be. Because that's his whole life story, is deep fried.
All right, so visual mapping. You might notice that this is an empty slide, and I'm going to do some finagling here and try to get this because the data we got off of BMIT couldn't really be formatted on a slide. So I'm going to do my best here with our setup. Okay.
If you need to, you can stop sharing, switch, and then start sharing.
Yes. All right. Bring it up. Oh, I know what happened.
I think you're just sharing that.
Yes.
Yeah, so you'll probably have to stop.
We're going to go there. We're going to go there.
There we go.
Yay. Okay. So what you are, oh, am I going to be able? Oh, it's going to be delayed. All right. Bear with me here. So what you're looking at right now is a cross-section slide of a chicken nugget that we took. So this is sample A, our non-emulsified nugget. And what we're seeing here is, in this denser area down here, we have the meat. We have if we're looking at a cross-section, we're looking at a sideways view of a chicken nugget cut in half. And we're looking at the dense area down here, which is just going to be our meat. And that won't really contribute to our crunch or crisp, but up here, what we're seeing is all of these pockets of air that are sitting within the breading section up here. And those are what we found this really interesting. But this is all the pores that you see, which are contributing to that dry crunch. Now, a little hard to see in the back of the room, but inside these full parts is our smaller sections of slightly darker pores, and what those are liquid crunch. And so looking at this, we can see a lot of separation and air pockets between these pieces of breading, but we're also seeing the oil sections that are also very full, and that's kind of why we believe we were getting that high level of crunch on that chicken nugget. And so as we're scrolling through, obviously this isn't a full picture of a chicken nugget, but what we're looking at here is tons of air that when you bite in, you're going to experience that as you chew through. You're going to rupture more and more of those pockets that are filled with air, and we're going to feel that all the way through that chicken nugget bite. And so kind of look through here. This was kind of what we found. And so, yeah, that was lining up with kind of our projected findings of what is going to make that crispy and why it's the correlation between the experience that we were hoping or that we experienced and the structure of it. Now, I'm going to do this one more time. Not the best saturation on this TV, but okay. So, because we were lucky enough to use BMIT, we were able to.
You're good. Okay, your mouse is gonna fall. My bad.
Get, in addition to that sideways or that cross-sectional scan, we were able to get our 3D rendering of a small piece of breading from that chicken nugget. And what we got here is this is kind of our base scan. So what we initially saw was there was air up here and there was air in here, and we removed those from the scan just to make those transparent. And what we're starting to see, you can't see it out here, is small pockets. There'll be a little bit more visible in a second, but small pockets of air and oil in here that are kind of showing up. And if we go a little bit further, why is the VSO not working?
Because they got the memo from the rest of the computers and we're going to have troubles today.
Come on. Give it 5 seconds, folks.
It's all good.
Okay, so what we did now was remove some of those exterior air pockets, and that leaves us with this. Now this is a bit more of a defined shape. You can start to see the pores really start to appear, at least on the outside structure. And obviously we've got larger pores over here, and what we're seeing is kind of a variation in pores, and those different sizes can help contribute to different types of crunch. Well, you'll feel it in different ways. We've got the large sections over here and the smaller sections further into that dense area of breading. And those are all contributing to that textural sensation. Kind of go around here, give you a bit more of a view. And one further, because what we're still seeing is a combination of our breading and our oil, which is all together in that mass. Now, we have obviously the air pockets, those are dry crunch, those are removed, but we don't have our wet crunch defined yet. And so what we'll do now is define it. Oops, not quite. There was a better way to do this. It's not working right now.
The way for chicken nuggets, this color, I don't recommend it.
Yeah. Okay, got it. All right. So what we have now is a removal of that oil. And what we're looking at now is all of those pores, be those dry pores or wet pores, simultaneously. Let me see if I can zoom in here. In our texture breading. And what we're seeing is tons of variation and tons of different sizes of pores and types of pores that are all contributing to a varied porosity. And that porosity is what we're going to experience on the bread. Now, what would have been great is if we had 3 of these. Unfortunately, due to a lack of time on part of our group, time on the beamline and time on different softwares for analysis on our data, and some issues with our motion artifacts on our other scans, we just weren't able to get those correlative data. And so we're a little disappointed about that, but we're still able to see kind of why this piece of Reading was able to give us the best crunch. And moreover, we were able to find why this piece, using the small piece of data that we could get off of the other two scans, that the raw data effectively looked very different and looked much flatter, much less dense, or so much more dense rather, than this piece of Reading, which had tons of pockets of air and different variations of texture. So that wasn't optimal, but we, just for reference, we as a group had the IDEAS beamline in mid-February, and we did our BMIT scan mid-March, and then we got this data, the 3D data, last Wednesday, so we've been kind of working with what we got. But with that said, this was kind of our finding, and we were able to really look at the pore structure of this piece of Reading at least, and we found that really reinforced our ideas coming into this of what we were going to find and what was going to contribute to our crunch. Going back here. These were kind of some of the references we used and what kind of gave us those initial ideas to drive this concept, this idea, and what gave us ideas as to what we could be looking for, and even the fact that throwing a chicken nugget in a giant X-ray is not as kind of ridiculous as it sounds. We'd like to thank Tracy. Obviously, she gave us our access to this in this course, and it's been really cool to kind of have that as an experience. Tor Peterson, who helped us on our IDEAS beamline and did some imaging for us, which he didn't have to do, and we really appreciate that. Zhao Fan and Adam who helped us greatly with our BMIT studies, and without them, this would have been entirely impossible. So thank you to them. That was greatly appreciated, and we got something because of them. So thank you for watching. Any questions?
Don't let her eat her hand.
Several. We did, but sample is a very small section of time. Some things are not samples once they're in different places. So
Boston Transit, right?
yeah, absolutely. You know what? It was a rough estimate.
Hi,
All right.
guess what? Chicken butt.
Thank you. And yeah.
To say congratulations to all of you. You did a really, really good job. I'm very proud of you. It's fantastic. Thank you, folks, for joining us. And thank you online for joining us. I'm going to kill the live stream now.